Why is quantum entanglement so hard to grasp? Imagine two particles that are connected in a way that no matter how far apart they are, what happens to one instantly affects the other. Sounds like science fiction, right? But this is exactly what quantum entanglement is. It's one of the strangest parts of quantum mechanics. The challenge is that it goes against everything we know about how objects should behave. In everyday life, objects are separate and have their own properties. But in quantum physics, particles can become linked so tightly that they act as one. This connection is called entanglement, and it's hard to understand because it defies our normal ideas of space and time. Let's start with how quantum particles are described. They are represented by wave function, which are like mathematical blueprints showing all the possible outcomes of measuring their properties. When particles become entangled, their wave function combine into a single, complex wave function that can't be split into parts. This means the particles are not independent anymore. If you measure one particle's property, like its spin or polarization, you instantly know the property of its partner, even if they are light years apart. This kind of instant link is called non-local correlation, and it's something classical physics cannot explain. It challenges the idea that nothing can travel faster than the speed of light. Before measurement, entangled particles exist in a superposition, meaning they hold multiple possibilities at once. Only when you measure one do the possibilities collapse into a definite state. When this happens, the other particle's state is fixed too, in a way that's perfectly correlated. This is very different from objects in classical physics, which always have definite states. The idea that measuring one particle instantly influences another makes it seem like information is traveling faster than light. But experiments show that no usable information is actually sent this way, so it doesn't break the rules of relativity. Scientists once thought there might be hidden variables, like secret instructions, that determine how particles behave. But experiments testing Bell's inequalities proved that these hidden variables cannot explain entanglement. The results confirm that entanglement is a real quantum effect, not just a trick or a coincidence. The math behind quantum entanglement is also part of what makes it tricky. It uses abstract concepts like Hilbert spaces and tensor products, which are far removed from everyday experience. These tools help describe how particles can be linked in ways that seem impossible in the real world. Entanglement isn't just a theoretical idea. It's the foundation of many emerging technologies, like quantum computers and quantum cryptography. Quantum computers use entangled particles called qubits to perform calculations much faster than traditional computers. This collective behavior allows for new kinds of processing power. Entanglement can involve many particles at once, creating complex networks that act as a single system. This many-body entanglement is still being studied and is key to understanding new materials and future quantum devices. So, the reason entanglement is so hard to grasp is because it goes against our everyday experience, involves complex math, and shows phenomena with no direct analogy in the world we see around us. Yet, it's a proven part of quantum mechanics and a vital piece of the puzzle for future technology.